Welcome to our lecture on topological bond structure theory. Today, we are going to talk about how topology arises in electronic structures, and in particular, how it helps us to understand several types of very exotic phenomena in electronic systems. So in particular, we are first going to start with the simplest topological state, which is the quantum Hall state. We will see why the transport in this state is topological and what is the origin of the edge states in the quantum Hall state. And most importantly, why topological states are resilient to perturbations, which is the most important property of topological matter. And afterwards, we are going to look at different types of topological states, both in one dimension and also in two dimensions, and show that they have topological invariance, that take a non-trivial value on the bulk, and associated to this invariant that they actually have gapless edge states. So in a more concrete way, this is essentially the things that we are going to address today. So first, we will look at linear response theory and how to compute the whole conductivity from linear response theory. We will then move on to quantum Hall effect and understand the origin of the edge states. And then we will think about a more general view on electronic states using the concepts of topology, that in particular will use the notion of the Chern number and the Sachs phase. And with these ideas in mind, we will move on to specific models of topological matter, including one-dimensional models and two-dimensional models. And finally, we will briefly comment about how we can get topological states of matter not only in electrons, but also in more generic type of excitations. As a reminder, let us just recall that in previous sessions, we saw that the Hamiltonian of a system, in particular of a single particle system, can be diagonalized, and it essentially, when we diagonalize it, we find a relation between the energy and the momentum. This relation between the energy and the momentum is the band structure, and the band structure can have many different forms. So it can give rise to a parabolic band, which is the most conventional one, and it can give rise also to flat bands, which is the case of the Landau levels in the quantum Hall effect. So today we are going to essentially try to see what is the internal mathematical structure of these band structures, and more specifically of the wave functions that form these band structures. This internal structure is essentially where topology arises, and we will see that this internal structure actually automatically matters when we start computing specific observables. So just to have an overall idea, I think that it's worth to just think about what are topological materials. So topological materials are systems that have protected surface excitations at the same time as some excitation gap in the bulk. We can have many different types of topological states of matter. We have the most common one, that is the quantum Hall effect, that can be seen in graphene and other two-dimensional electron gases. But then we also have more exotic types, such as the quantum anomalous Hall effect, which is effectively like a quantum Hall effect in the absence of a magnetic field. We can have also quantum spin Hall insulators that are effectively two copies of the quantum Hall state, one being the time reversal of the other. We can have superconducting versions of topological matter, such as topological superconductors, that are incredibly important for topological quantum computing. And we can also have more sophisticated topological states, such as topological semimetals, including Weyl semimetals that give rise to Weyl fermions. And even we can have topological states in systems that are dominated by many-body interactions, such as topological conductors, and many others that do not fit in this slide. What is important is that topology and topological excitations appear in many materials in nature, and they are a very interesting platform to see excitations that do not appear in the absence of topology. Okay, then let's move on and let's start thinking about how some geometric properties of wave functions can actually matter when we make a measurement in a material. And to understand this, we are going to use the most straightforward approach to compute measurements, which is called linear response theory. And with this, we will see that the whole conductivity, it's actually a topological invariant of the electronic structure. The idea of linear response theory is relatively simple. So imagine that you have a certain material that here is this gray rectangle. And in this material, you do the following. You create some perturbation in a certain position x as a time t, and then at another position x prime and time t prime, you make a measurement. This measurement can be the charge, can be the current, can be magnetization, can be heat, can be anything. The idea of linear response theory is that it allows us to predict what is the measurement that we will see in the position x prime and time t prime as a function of the perturbation in x and time t. And this expectation value effectively just depends on the electronic structure of the material. This idea of linear response theory is actually extremely powerful, and it allows us to understand many different observables in materials. So for example, if you put different impurities in a 2D metal, and you look at how the electronic density gets modulated or how the local density of state is modulated, what you actually get from perturbation theory is that this modulation depends on the Fermi wavelength of your electronic gas. So just by looking at how these perturbations are in space, you can read what is the Fermi wavelength of your two-dimensional electron gas. And it's something that it's systematically done in metals, for example, with STM. Then another case where linear response theory appears very naturally is when you measure neutron scattering in materials. So you just throw neutrons towards a magnetic material, the magnetic moment of the neutron interacts with the local magnetic moment of the material, and the scattering between the neutron and the material allows you to essentially reconstruct what is the magnetic structure of the magnetic material. And not only the magnetic structure, but also the magnetic excitations that you see in the material, in particular, magnons. Neutron scattering allows you to directly see magnons in three-dimensional materials. And the idea behind this is just linear response theory, essentially the perturbation that you create on the magnetization when the magnetic moment of the neutron interacts with it. Okay, so for linear response theory, we essentially need to follow a relatively general idea. So we have our original Hamiltonian of the material that it's H0. This is the Hamiltonian of the unperturbed material. So before we actually make any sort of perturbation in the material. And then when we make the perturbation, that can be, for example, adding a small magnetic impurity or adding a local magnetic moment on one side, our Hamiltonian gets modified. And this modification is essentially what we parameterize as lambda v, where v is the perturbation and lambda is essentially a control parameter that allows you to essentially say how strong or weak the perturbation is. The idea of linear response theory is that if you have a small perturbation, you do not need to solve the Hamiltonian that it's the original Hamiltonian plus their perturbation. You can express the solution of that Hamiltonian using just a Taylor expansion around the original Hamiltonian. So you can think that you are essentially expanding in terms of a, let's say, power expansion, any observable that you see. So more concretely, the idea is the following. So you take your Hamiltonian H that depends on lambda. Lambda controls the strength of your perturbation, and you can expand every single observable in your material as a function of this lambda. For lambda equal to 0, you recover the original Hamiltonian. For lambda equal to 1, you obtain the Hamiltonian in the presence of the perturbation, and you can try to express everything. So the energy as a function of lambda, the observables, including the electronic density or the local magnetic moment or the current as a function of lambda, or even the wave functions themselves as a function of lambda. And we effectively just have to do a Taylor expansion of any of these terms as a function of lambda. And essentially all the observables in linear response theory come from this Taylor expansion. So the idea is that when you, let's say, put a certain perturbation that can be, for example, a local charge in a very specific position x, then you can try to compute the density in some other position x prime as a function of the perturbation that you put in x. So the idea is that you essentially express the observable that you want to measure as a function of lambda, and then you expand every single object as a function of lambda. So your wave functions, your observables, and in particular, the derivative of the observable with respect to the strength of their perturbation is what you call the response of the system. And that is the fundamental object that you obtain from linear response theory. In a more concrete way, this response of the system is what we usually call the susceptibility of the system, the magnetic susceptibility of a magnetic material, for example. So in practical terms, when we want to compute a certain observable, maybe the most important object for us is the wave function of the material, because if we have the wave function, we can essentially compute any observable that we want. So in practice, the most important object to perform an expansion is the, let's say, ground state wave function of the material. And for this case, we can just use a Taylor expansion that says that the wave function for material is our original wave function plus lambda, and then a certain set of coefficients times all the other possible wave functions, in particular single particle wave functions that are orthogonal to the original wave function. So the actual task is to find this expansion coefficient, so this alpha j. And the idea is that these expansion coefficients can be computed very easily just by doing a Taylor expansion of the Hamiltonian. And what you actually get is that the coefficients are essentially given by this overlap between psi I, V, psi j over the eigenenergies I and eigenenergies j. And for most of the formulations of linear response theory, you essentially get that there's a term in the expansion that looks like this, and it comes, of course, from the expansion of your coefficients. So the bottom line is that using this, let's say, low coupling expansion, we are capable of expressing the perturbed wave function of a Hamiltonian, the perturbed eigenfunction of a Hamiltonian as a function of the unperturbed wave functions of the Hamiltonian. Okay, so far we have assumed that when we add a small perturbation to a Hamiltonian, then everything can be Taylor expanded. So meaning that if we add a small perturbation, then the result has a small perturbation with respect to the original result. This is called the perturbative regime. So the regime where a small perturbation in the input creates a small perturbation in the output, meaning that the input is your charge in position x and your output is the charge in position x prime. This doesn't have to be the case for every single quantum material. And we will see during the course that there are cases that are non-perturbative. And in particular, there are several famous cases that where perturbation theory does not hold, or at least the simplest form of perturbation theory. And this is the case of, for example, when you add an impurity to a metal that gives rise to something that is called orthogonality catastrophe, that effectively makes all your wave functions automatically orthogonal to the original wave functions, even with a very small perturbation. Another case that is very much related with this one is the case of a quantum spin in a metal that gives rise to the Kondo effect. And the Kondo effect is also a non-perturbative effect in quantum many-body systems. And in particular, the Kondo temperature is non-perturbative on the actual coupling between the Kondo impurity and the electron gas. And then another case that it's, of course, very important is the case of superconductivity, where the superconducting order is also non-perturbative on the actual, let's say, many-body interaction. So we cannot use perturbation theory in this case. These cases are going to be very important later in the next lectures, but for today's lecture, we are going to assume that perturbation theory holds, and for the models that we are going to study, it certainly holds. Okay, so now here's the case where we are going to use perturbation theory. And this type of measurement is essentially called the transverse conductivity. It's called the Hall conductivity. So the basic idea is that we are going to take a two-dimensional system, and in this two-dimensional system, we are going to apply a voltage in the y direction, and we are going to ask ourselves what is the current in the x direction. So we are going to have some original Hamiltonian for this material that is going to be H0. The perturbation that we add to this Hamiltonian is a voltage in the y direction, that it's essentially y, or if you write it in momentum space, derivative with respect to ky, and then our observable is the current in the x direction, that in practice you can write as the derivative of the Hamiltonian with respect to kx. In practice, this can be done in an experiment just as we saw in the drawing. So one can actually put a voltage between the left and right side of a material and then measure what is the current in the transverse in the perpendicular direction. And then the relation between this voltage and this current is the Hall conductivity. And linear response theory allows you to explicitly compute this Hall conductivity using perturbation theory, and of course, starting with the wave functions of your unperturbed regime. Now, if you just directly apply the formula for perturbation theory that we saw previously in the definition of the, let's say, Hall conductivity, you automatically get this expression that you see here. So this expression, of course, can look a little bit complex, but you can very easily recognize that we have the 1 over epsilon alpha minus epsilon beta that comes from the expansion of the wave functions. And we have the derivative of h with respect to kx that it's essentially the velocity, that, in other words, the current. So you obtain this formula directly plugging the definition of perturbation theory that we get for the wave functions onto the definition of the Hall conductivity that we saw in the previous slide. And what is interesting is that one can actually just write this Hall conductivity as an integral over the Brillouin zone, so as a sum over all the states in the reciprocal space of this very specific object. Now, maybe the most interesting thing is that this very specific object can be rewritten in a way where there's no explicit dependence on the actual energies of the system. So one can use this relationship of psi derivative of h with respect to k, psi that it's equal to the derivative of the wave function times the wave function and the difference between the energies to rewrite the previous expression. And when you rewrite the previous expression, you can actually see that the Hall conductivity can be rewritten as a function of an object that only depends on matrix elements of the wave functions and not at all on the energies. And this is the most important point about the Hall conductivity. The Hall conductivity is an observable that do not depend on the actual energies of your band structure, but only depends on the wave functions themselves. Meaning that you can add perturbations that change the band structure of your system. As long as the wave functions do not change, then the Hall conductivity is going to be the same. And then there's an even more important point about the Hall conductivity, which is that due to the definition that it has as a function of the wave functions, one can actually show that it can only be an integer number for systems that have a gap. So if you have a system that it's not a metal, that it's an insulator, the Hall conductivity must be an integer, irrespective of any detail of your band structure, irrespective of how your dispersion is, irrespective of whether if you have, let's say, 10 bands or 20 bands, you are always going to get an integer. And this is in a way related with the fact that your reciprocal space is actually a compact manifold, that it's a torus for a two-dimensional system. And this idea of, let's say, having a closed surface automatically gives rise to an integer Chern number, just because of matching of wave functions at one side of the Brillouin zone and the other side of the Brillouin zone. This is the first encounter of a topological invariant when making a measurement. The Hall conductivity is an integer, and this integer is a very specific topological invariant called the Chern number. And in particular, this Chern number appears very naturally in the case of the quantum Hall state. So in the quantum Hall state, that it's effectively the case that you obtain when you have a two-dimensional electron gas and you apply a perpendicular magnetic field, what we will see is that we essentially have an electronic structure that consists of flat bands. So a band that has no dispersion whatsoever, and we have a different set of states. So we have sets for, let's say, the first Landau level, the second Landau level, the third Landau level, and so forth. The most important point of these flat bands is that they are actually topologically non-trivial, meaning that if you compute the Chern number of a flat band, you get that the flat band has Chern number 1. Now, if you put your chemical potential in between the first flat band and the second flat band, then you have one band that is filled and that has Chern number 1. If you put it above the next band, you have now 2 bands filled with Chern number 1, giving rise to a total Chern number 2, and so forth. So in the quantum Hall state, depending on where your chemical potential sits, you will have Chern number 1, or Chern number 2, or Chern number 3, and so forth. So you have a collection of states that are all insulators, but that they can have a transverse Hall conductivity that is quantized and quantized in different integers, 1, 2, 3, and so forth. Now, a very important question is, well, we have an insulator, and an insulator has a gap, but the transverse Hall conductivity is a conductivity. So there has to be some electron that is capable of moving around. If you have an insulator, we tend to think that there's no current going in the bulk, and therefore there has to be some current somewhere to account for this quantum Hall conductivity. The actual point that happens is that if you have a real system, you of course always have a boundary. So there's some point where your material finishes and you no longer have bulk. In a quantum Hall state or in a material that has a finite Chern number, what actually happens is that at this edge, you have gapless edge states. And you can think that the states that actually contribute to the Hall conductivity are these states that are living at the edge. So the quantization of the Hall conductivity is effectively associated to the existence of these gapless edge states. There's something actually very important of these gapless edge states, and it's that the states that you have on one edge, they propagate in a single direction. So if you think about the top edge, you have a state that propagates to the left, but there's no state that propagates to the right in the top edge. And in the bottom edge, you have a state that propagates to the right, but there's no state that propagates to the left. The existence of a state that propagates only in one direction, it's what is called a chiral state. And this chirality in the surface states is essentially the reason why the transport in a quantum Hall state is protected. If you put an impurity, there's no state to which this propagating state can scatter to, and therefore there cannot be a loss in the conductivity. But we will look at this more in detail later on. So if you think about the electronic structure of a quantum Hall state, essentially what you get is something like this. So we have a set of flat bands that are the bands that live in the bulk, that are called Landau levels. And then at the edges of the system, we have states that propagate in one direction, one edge, and states that propagate in the opposite direction in the other edge. And these states are the ones that actually contribute to the Hall conductivity because are the ones that cross the chemical potential. We can look at, let's say, a very simple model that has this quantum Hall effect just by taking a tie-binding model in a square lattice and adding a magnetic field. You can do this with the library that we use for the calculation. So you can take a square ribbon, add a magnetic field, and see how the band structure looks like. And what you get is the picture on the right. And what we see here is that there's a set of flat bands that live in the bulk that are colored in green. And then at the edge, there are states that propagate in one direction in one edge and in the opposite direction in the other edge. And so if you want to look at the part where you essentially have originally parabolic electrons, you would need to look just at very low energies, close to energy equal to 0. And if you zoom in there, you essentially see that the spacing between the flat bands is roughly the same at low energies, and that, of course, you have your edge states that propagate in one direction, one edge, and propagate in the other direction, in the other edge. We will look at this more in detail in the next lecture about the quantum Hall state. Okay, so we have encountered the first case of a topological state of matter that was essentially looking at a two-dimensional electron gas, applying a voltage in one direction, measuring the current in the perpendicular direction, and we saw that that conductivity is quantized, and it depends on something called the Chern number. Now let us see if this idea of a topological invariant appears in other cases, or at least in other dimensions and in other types of band structures. The idea of topology is it's relatively simple, and it is based on the idea that if you have certain objects, you can start asking yourself which are the objects that can be smoothly deformed onto another without doing something dramatic. So, for example, you can think that you have some, let's say, flexible surface, and that you can deform this flexible surface, and then you try to classify all the different forms that can be deformed onto each other, so that you say, well, all these classes of forms can be deformed onto each other, all these classes of forms can be deformed into each other, and so forth. So a very simple example of this is taking, say, three-dimensional surfaces and classifying the surfaces according to how many holes they have. And it is relatively easy to understand that if you have a different number of holes, you probably cannot deform them onto each other, because deforming them would imply that you would close these holes. One can also think about some one-dimensional analog, and you can think about, let's say, lines that are closed, and you classify these lines according to how many knots they have. And if the knots are inequivalent, then you cannot transform the curves onto each other, and if they are equivalent, you can transform the curves into each other. Topology in general tells you which objects can be deformed onto each other and which objects cannot deform onto each other. And if you think about the case of the transverse Hall conductivity, you saw that the Hall conductivity depended only on how the wave functions were connected to each other. So there was no dependence on the energy, but there was only a dependence of how the wave functions changed in reciprocal space. You can think that the deformation in the case of Hamiltonians is actually changing the band structure. And so topology is actually a way of telling us which Hamiltonians can be deformed onto each other without closing the gap and which Hamiltonians cannot. Okay, so if we think in terms of surfaces, which is perhaps the most important case for us, you can think that, for example, there are two surfaces that are, let's say, relatively equivalent. So a donut has a hole, and a cup also has one hole, and you can actually transform a donut into a cup if you think that your, let's say, surface is flexible and it allows you to just, let's say, displace it and move it around. Whereas a sphere is not equivalent to a donut, or not equivalent to a cup, because it doesn't have any hole. And so if you think that it's this, let's say, sphere is, for example, filled with air, then you cannot, let's say, easily transform a sphere into a torus or into a donut, let's say, without actually breaking your surface. And in this way, we say that the donut is topologically equivalent to the cup, but they are topologically inequivalent to the sphere. This idea of topology in Hamiltonians can be phrased in a, let's say, precise way in the following way. So you imagine that you have a Hamiltonian that depends on the momentum. So this Hamiltonian that depends on the momentum gives rise to wave functions that depend on the momentum. These wave functions that depend on the momentum can be associated, or they are associated to a specific curvature that is called the Berry curvature. That is the very same object that appeared when we computed the whole conductivity. And if you integrate this Berry curvature in the whole Brillouin song, you get a topological invariant. And in particular, you get the Chern number that was effectively the whole conductivity of our system. The way we count the number of holes that we have in a Hamiltonian is directly through the Chern number. So Hamiltonians that have the same Chern number can be deformed into each other. Hamiltonians that have different Chern numbers cannot be deformed onto each other. So the Chern number is a topological classification of the Hamiltonian. It tells you which Hamiltonians are equivalent and which Hamiltonians are not equivalent. And so Hamiltonians with different Chern numbers, they cannot be transformed onto each other. So if you have a Hamiltonian with Chern number 1, there's no transformation that you can make to the Hamiltonian without closing the bulk gap that allows you to get a Hamiltonian with Chern number 2. And this has a really, really important consequence. Imagine that you have an interface between two Hamiltonians, Hamiltonian number 1 that has Chern number 0, and Hamiltonian number 2 that has Chern number 1. If you think now about defining a local Hamiltonian, so a Hamiltonian that changes in space, so when you are in the very left, it is H1, when you are in the very right, you have H2, then the fact that you cannot transform these Hamiltonians onto each other without closing the band gap automatically tells you that you are going to have a gap closing in the middle. There's no way of going from H1 to H2 without closing the gap. And therefore, irrespective of how this interface between H1 and H2 is, you are always going to have a metallic state over there. You are always going to have a topologically protected excitation over there. And in practical terms, we say that a Hamiltonian that has Chern number 0 is a topologically trivial system. And so, for example, the vacuum is topologically trivial, and a state that has Chern number 1 is topologically non-trivial. So now if you think about the case of the quantum Hall state, you can think that Chern number 0 is essentially the vacuum, Chern number 1 is your quantum Hall state, and therefore at each interface between vacuum and the quantum Hall state, you are going to have a gapless edge state. And this is the argument to understand the origin of topological excitations in interfaces between topologically inequivalent systems. So this idea of having a topological excitation between topological equivalent systems applies to any different topological invariant. It applies, of course, to Chern numbers, which is the case that is relevant, or that was the most relevant one when we started today, but it will also apply to different other types of topological invariants. And as mentioned before, the existence of edge states in the quantum Hall state can be associated to this non-trivial invariant of the quantum Hall state. This has a very important consequence, which is that irrespective of how the interface is between the two inequivalent states, we are always going to have an edge state. And so, for example, you can think that you start with a, let's say, perfect edge that has a chiral mode that has your topological excitation, and then afterwards you put an impurity, you put a perturbation on this edge. When you put the impurity, you are effectively modifying the interface between your topological state and your vacuum. But since the topological excitation needs to appear irrespective of this interface, then what actually happens is that your edge state reconstructs itself, your edge state heals itself, and it just goes around the impurity. And this protection is what guarantees the quantization in the quantum Hall state, and what guarantees the quantization of the topological state. The quantum Hall state is just the simplest case of a topological state of matter, and more generically, it is a very specific case of what are called Chern insulators, which are systems that have a finite Chern number. All Chern insulators have a finite Chern number, and this finite Chern number gives rise to chiral edge states. And these chiral edge states are, of course, protected under scattering, so they cannot actually have electric losses, and therefore they could be extremely interesting for electronic applications because they wouldn't have heating. There are, of course, other types of topological states, and in particular, there's one very special that it's called the quantum spin Hall state, that in practice consists on two copies of a Chern insulator. You can think that you have one Chern insulator for spin up, and then you have the opposite Chern insulator for spin down. In quantum spin Hall insulators, excitations are not chiral edge states, but they are helical, meaning that spin up propagates in one direction and spin down propagates in the opposite direction. This idea of having helical states is actually very useful for spintronics, because these helical edge states would allow to have spin transport with no electric losses, which of course are one of the most important ideas for spintronic applications. And then we have also other topological states that are even more exotic. So they do not only appear in electronic systems, they also appear when we have superconductivity. And this is the case of topological superconductors. Topological superconductors are superconductors that have an excitation gap on the bulk, but that at the surface or at the edges, they show gapless superconducting excitations. And these superconducting excitations are called Majorana excitations. They are excitations that are their own quasi-particle. And they are extremely special because these Majorana excitations would allow to perform topological quantum computing. They would allow to perform quantum calculations or quantum computations where the coherence is not actually effective. You don't have a decoherence in your algorithm because information is stored in a non-local way in your superconducting state. And conventional decoherence channels are not actually affecting the quantum information stored in the superconductor. Okay, so then let us move on to a minimal model for a topological superconductor, which is for a topological insulator, which is the SSH model. The SSH model is the simplest model to understand topological excitations. And even though it is a model that looks a little bit artificial, it is going to be very important later on for topological superconductivity. So the simplest model for topological superconductivity, which is the KTF model, is actually equivalent to this SSH model. Okay, so we are going to take a one-dimensional lattice. We are going to take a one-dimensional chain. And this one-dimensional chain is relatively special. So instead of having one site per unit cell, we are going to have two sites per unit cell. And we are going to take the extreme case where the chain is dimerized, meaning that we have gap between 0 and 1, we have a hopping between 0 and 1, hopping between 2 and 3, hopping between 4 and 5, but we don't have hopping between 1 and 2, and we don't have hopping between 3 and 4. So if you write it in second quantization, you would have something like C dagger 0, C1, C dagger 2, C3, and so forth. So maybe the first question to ask yourself is, well, what is the eigenbasis of the Hamiltonian? What is the spectra of this Hamiltonian? And if you think a little bit, you will actually figure out that the eigenstates or the eigenenergies are actually plus minus 1. So you effectively have dimers that are decoupled. And when you have these decoupled dimers, essentially the eigenenergies are the eigenenergies of each dimer individually. And so you have bonding and anti-bonding states that have energy plus minus 1. We can think about a dimerized chain, but that it's sort of shifted by, let's say, one site. So the first site is decoupled from everybody. Then we have sites number 1 and number 2 that are coupled, sites number 3 and number 4 that are coupled, and then site number 5 is also decoupled from everybody. So this is sort of the same system as the previous one in the bulk, but at the edges it's slightly different. So these sites that are not coupled are called dangling sites. Now, if you ask yourself, what is the excitation spectra of this Hamiltonian, you can actually see that, well, the excitation energies now are 0 and plus minus 1. So plus minus 1 for the sites that are coupled. So again, we have bonding, anti-bonding states, and for the sites at the beginning and at the edge, we essentially have 0 energy modes. This dimerized chain is sort of a very simple case of a topological state. You can think that this Hamiltonian has two different phases. Phase on the top, that is the trivial phase that has a gap everywhere, and then the phase on the bottom, that is the topological phase that has a gap on the bulk, and that it has gapless excitations on the edges. Of course, this seems like a, let's say, very fine-tuned model and even perhaps a little bit, let's say, unrealistic model, right? Because usually we are going to have couplings between all the sides. What is actually important is that this idea of having a gap in the bulk and gapless excitations on the edges survives even if you put some small couplings between the sides that are originally uncoupled. And this is something that we can check, and we will check during the exercises, and you will see that actually we have gapless edge states that are robust to this small perturbation that couple all the edges. So in practice, we can think that this model has these two phases. So the phase that it's trivial, that has gap everywhere, the phase that is topological, that has gap in the bulk, and gapless edge excitations. Now, let us come back to this idea of coupling all the sides. So if you think now of the topological phase and you add some small t between the sides that were originally uncoupled, then you can start asking yourself, well, do these edge modes survive, or do they just disappear when I add this coupling? And what it turns out is that even if you couple sides 0 to 1 and sides 5 to 4, then the surface states survive. There are several ways of thinking about it. You can think that if t is much smaller than 1, you are essentially coupling a zero mode to an insulator, so the zero mode is going to stay there. And you can also think that you can actually deform these Hamiltonians onto each other. So you can show that they are topologically equivalent. This can be actually made much more concrete just by looking at the block Hamiltonian of the system in the presence of this coupling T. So you can start asking yourself, well, how should I write the block Hamiltonian for this? So I'm going to have a 2x2 Hamiltonian that has off-diagonal terms because of how the geometry is. And when you write the Hamiltonian, you will see that you essentially get something like this. So 0 in the diagonals because there are no one-side energies. And then in the off-diagonal term, you have your t and e to the ik. Now, you have this 2x2 Hamiltonian, and you can start asking yourself, well, what is the wave function that I can get from this Hamiltonian, and how can I classify the topology of these wave functions? So the wave function for this Hamiltonian, in particular at lowest energy eigenfunction, is going to be psi k. And for a Hamiltonian that has a single parameter, one can define a relatively simple topological invariant, which is the so-called SAC phase, which in practice, it is just wave function derivative with respect to k of your wave function and integrate it in the whole Bernoulli zone. This topological invariant essentially counts how many times your phase winds around the origin. So you can think that this object A, which is the very connection, essentially extracts what is the phase of your wave function. And then when you integrate the phase of the wave function over the whole Bernoulli zone, you are essentially counting how many times it's going around the origin. And this how many times is winding around the origin is exactly a topological invariant. You can think that it's equivalent to the number of knots that you have in a one-dimensional line. And you can actually do this integral very easily. And you can easily show that if t is bigger than 1, then the phase doesn't wind around the origin, and the very phase that you get at the end is 0. So this is essentially a trivial insulator, whereas if t is smaller than 1, then the phase winds around the origin just once, and you get a topological insulator. And in particular, you get a very phase that is plus minus pi. The very phase, or the SAC phase, is the topological invariant for this type of one-dimensional models. And in practice, if we have a system that is trivial, we will have a very phase of 0 and no edge states associated to this very phase. Whereas if you have a system that is topological, then the very phase is going to be plus minus pi, and we are going to have a gapless edge state. So there's going to be a one-to-one correspondence between the value of the topological invariant, the value of the very phase or SAC phase, and the existence or absence of a gapless surface state. We have seen before a one-dimensional topological model. Now let us move on to two-dimensional topological states. And of course, there's one topological state that we already considered, that is the case of a Chern insulator or quantum Hall insulator, which is the case where we saw that the whole conductivity is a topological invariant, and that it was related to the Chern number of the system, and that the Chern number of the system was actually computed by integrating the very curvature, and that the very curvature depended on the wave functions in reciprocal space. Chern insulators have chiral modes, and what's most important is that they need to break time reversal symmetry. If you go back to the formula of the Hall conductivity, you can very easily see that the Hall conductivity is exactly 0 if you have time reversal symmetry. So now one question is, can we have topological states even when time reversal symmetry is present? And the answer is yes. And the simplest way of having a topological state in the presence of time reversal symmetry is by having opposite Chern insulators for spin up and for spin down. This is the case of a quantum spin Hall insulator. You have a system that has a gap on the bulk and has gapless surface states, in particular helical states, where spin up propagates in one direction and spin down propagates in the opposite direction. And what is most important is that by having this combination, you don't break the net time reversal symmetry of the material. Okay, let us now look at Chern insulators and see how we can actually get that Hall conductivity that it's finite even when we don't have, let's say, Landau levels. So as we saw before, the Chern insulator is a state that has a finite Chern number, and that the Chern number can be computed by integrating the very curvature that in turn can be computed from the very connection that is written over here. One can think about many different low energy models that have a finite very curvature, but let me present one of them. And this model is essentially based on a gapped Dirac equation. So now let us imagine that we have some specific two-dimensional model that has a Dirac equation, like for example, the honeycomb lattice or the Kagome lattice, or maybe a square lattice with pi flux. This Dirac equation can have a mass, and this mass is essentially the m parameter that you see in this equation. So the Dirac equation is px sigma x, py sigma y, m sigma c. Px and py are our momenta. So if you now compute what is the Chern number of this Dirac equation, and for that you just need to compute the eigenstates, from the eigenstates the very curvature, and then integrate the very curvature, what you actually will see is that the Chern number is 1/2 times the sign of your mass times the sign that you have in front of the sigma y Pauli matrix. If you have a bond structure that features Dirac equations with a gap, then you have a local Chern number. And of course, one of the lattices that shows this Dirac equation is the honeycomb lattice. So if you take the honeycomb lattice and you open a gap in the Dirac points by breaking time reversal symmetry, then you will get a Chern insulator. And there are, of course, many ways of breaking time reversal symmetry in the honeycomb lattice. One way of breaking time reversal symmetry is by applying what is called the Haldane coupling, which is a second neighbor imaginary hopping. This second neighbor imaginary hopping is effectively equivalent to a local internal current, and this opens up a gap, gives rise to a local Chern number plus minus 1/2 in each Dirac point, and give rise to a net Hall conductivity of Chern number 1. This Haldane model was the first model that was proposed where one would have a finite Hall conductivity in the absence of a magnetic field. And then, of course, one can open gaps in these Dirac points in other ways. So if you consider that you have, let's say, honeycomb lattice that has both magnetism and spin orbit coupling, you effectively also end up with a gap at your Dirac points. And this gap also gives rise to a anomalous Hall state, to a Chern insulator. Now, these are, of course, low energy models. So one can ask how relevant are for materials. And let me emphasize that even though this is, of course, just a toy model, something equivalent to the Haldane phase can actually be realized in materials, and in particular in twisted graphene bilayers on top of boron nitride, and then something equivalent to the honeycomb lattice with magnetism and spin orbit coupling is realized in magnetically doped bismuth selenide, which is one of the materials that was shown to feature a quantum anomalous Hall state. And so in general, if you look at the electronic structure of a Chern insulator, and in particular the honeycomb lattice with a Haldane gap, what you will see is that you have a gap in the bulk. So you have your gapped Dirac equations, but then when you look at the surface of your material, you see that there's one state that propagates in one direction. And of course, if you go to the other surface or to the other edge, the state propagates in the opposite direction. Okay, let us move on now to the quantum spin Hall state, quantum spin Hall insulators. So in practice, the idea of a quantum spin Hall insulator is to have a Chern insulator with opposite Chern numbers for each spin. So you can think that you can define a Chern number 1 for spin up. This gives rise to states that move in one direction throughout the edges. And then for spin down, you get a Chern number -1. Of course, a very important question is what could be the mechanism giving rise to opposite Chern numbers to opposite spins? And the answer is actually relatively simple. So if you look at the form of spin-orbit coupling, this is the relativistic term that appears in the dynamics of electrons due to the coupling between angular momenta and spin. What you actually get is that there's something that looks like L dot S. And if you focus on the third component, you have something that it's LCSC. A way to look at this term is by understanding that this LCSC is like a positive magnetic field for spin up and a negative magnetic field for spin down. So spin orbit coupling acts as a positive magnetic field for one spin species and as the opposite magnetic field for the other spin species. And this idea of having opposite, let's say, magnetic fields or opposite breakings of time reversal symmetry for one spin then the other spin is effectively what one needs to get a quantum spin Hall state. And quantum spin Hall insulators are effectively just driven by this relativistic spin orbit coupling in materials. So in a quantum spin Hall insulator, we effectively have just two copies of the Chern insulator. And in each edge, we have states that propagate in one direction for spin up and the opposite direction for spin down. So, of course, a very important question now is what could be the model that gives rise to a quantum spin Hall state? And for this, we can just go back to the model that we used for a Chern insulator and just make two copies, one for spin up, one for spin down. So we write down again our model that it was a Dirac equation with a gap. As before, the Chern number for one spin species and one valley is 1/2 sine of the mass sine of the sign that we have in front of ky. And if we now assume that opposite spins have opposite masses, we effectively end up with an electronic structure that has a total Chern number equal to 0, because we do not break time reversal symmetry, but a spin Chern number that is ±2. And this mass that depends on the spin channel can be effectively generated by spin orbit coupling. And in the case of graphene, that is what actually happens. So graphene itself is a quantum spin Hall insulator. It has a very, very small gap, but it is a quantum spin Hall insulator. And so something that is very important about quantum spin Hall insulators is that the invariant itself is not only protected by, let's say, the independence of spin up and spin down. So far, we assumed that we could define a topological invariant for spin up, we could define a topological invariant for spin down, and in that case, we would have gapless edge states. But something that is worth asking is, well, what if you have spin mixing terms that mix spin up with spin down? The way to understand this is the following. Let's start with the case where there's no spin mixing. So we have a independent Chern number for spin up and Chern number for spin down. In that limit, we are going to have the gapless edge states that you see in this picture. Now, you can start switching on these spin mixing terms. These spin mixing terms, if they respect time reversal symmetry, they must give rise to a degeneracy that is compatible with time reversal symmetry. And in particular, now it is important to remember that the time reversal symmetry operator for spinful electrons squares to -1. What this actually implies is that in the points in the Brillouin zone that are time reversal symmetric, in particular the gamma point and the X point, one needs to have twofold degeneracy. In the absence of spin mixing terms, the twofold degeneracy is guaranteed. Now, once you switch on spin mixing, then if you have time reversal symmetry, the twofold degeneracy must remain there. What this actually means is that even perturbations that mix a spin will not break the degeneracy that you have at the X point, will not open a gap in your edge states. So in a quantum spin Hall insulator, the gapless states are actually protected by time reversal symmetry, by the idea that you have Kramer's degeneracy at the points that are invariant under time reversal symmetry. And of course, there are several examples of quantum spin Hall insulators. One of them is graphene, as mentioned before, but perhaps the most important one is 1T tungsten ditelluride, which is a quantum spin Hall insulator where quantum spin Hall effect can be seen up to 100 Kelvin. Okay, now this idea of topological protection, the quantum spin Hall state can be addressed more specifically just by seeing what happens with the electronic structure once you put impurities. So if you start with a quantum spin Hall insulator without impurities, you have your gapless edge states that you see on the left. If you now start adding disorder that does not break time reversal symmetry, you have the band structure on the right, on the center. So your band structure got modified, but you still have gapless edge states. But if you now add disorder, then your edge states open up a gap and you no longer have gapless helical modes. So quantum spin Hall insulators are resilient to disorder that does not break time reversal symmetry, but they are actually not resilient to disorder that breaks time reversal symmetry. And now, as a last point, let me mention that these ideas about topology not only apply to electronic structures. We have, of course, focused on models for electrons in quantum materials, but all these ideas of finite Chern number, finite Sachs phase, and many other topological invariants can be applied to many different types of quantum excitations. So electrons, of course, but also magnons in quantum materials, spin-ons in quantum materials, and many other quantum excitations. We will look at some of those examples in the next few lectures, but beyond quantum excitations, it is also worth noting that topology also appears in systems that are not exactly of electronic nature and perhaps even not quantum. So you can actually have topological modes in photonic systems. You can have topological modes in systems that just have photons traveling through a material, or in systems that they just have vibrations, and they do not have to be described with a quantum formulation, but also classical vibrations can be topological. And the basic idea is that every time that you have a dispersion relation, so a relationship between energy and momentum, topology may appear. And this relationship between energy and momentum is something that appears everywhere in physics. Every time that you have a propagating wave, there's a relationship between the frequency of the wave and the momentum of the wave. So any physical system featuring waves, photonic systems, classical mechanical systems, and of course any quantum system can feature topological excitations. And this has been a very interesting direction in the last few years, where people actually showed that tabletop experiments that are macroscopic actually show topological excitation, like, for example, sets of penduli that are coupled to each other, or even, let's say, actual circuits that you can build in the lab, they can have topological excitations. Okay, this is everything that I would like to tell you today. So if I can ask you to remember something, please remember that topological systems have protected edge modes that are associated to a non-trivial topological invariant, and that we can have topological states in 2 dimensions, 1 dimension, and that they are often protected by a very specific symmetry. Thank you so much for your attention.